Thanks for this opportunity. It's a very successful, very intense and interesting meeting conference. So I'll tell you about some things which can be exactly solved in out of equilibrium in the context of CFTs. And this is a work which is based on 2 papers and some ongoing stuff. So this is the first paper was with Rupayan, who is a postdoc at UC London, Krishnendu Sengupta, who is at Cultivation of Science, and the second part of the talk will be on some work that we finished recently, and we are continuing with Sumit, Arnav and Krishnan. So the main question that we'll try to address, so this is a difficult question, and in some very special corner we will find some answers. So which is that if I have a out of equilibrium situation in a quantum field theory, then so the way I will take it out of equilibrium is through a time dependent coupling, or one can think of changing the Hamiltonian in time. Then what is the time development of observables? In particular, does at late times is there any steady state description of the final density metric, so that we can know what to expect when we do measurements. A very general question, and it will be posed in this setting of which is one of the settings where a lot of explorations have been done, which is where one has 2 Hamiltonians, H0 and H1, which are different, and they alternate between each other. And there is a periodicity, as you can see. So there is a discrete time translation symmetry which simplifies certain things. In particular, the evolution operator, after n cycles, one can write it like this. So within a time period t0 to t1, you first evolve by H0, then by H1, and then you just repeat this. And this scenario is called the flow K. And this will be the setup which we will work with in CFTs. So I will first, so this is the outline. So I will first discuss this setup. So to begin with, because a lot of work has been done already in 1+1 dimensions, so the playground will be 1+1. And then we'll see how the exact dynamics looks like, and we'll try to understand the dynamics from some geometric point of view. So this is, I will not be talking about anything in context of holography. This is just the geometry of the transformation. And then so from this block we will go to some smooth. So this is discrete, but one can go to some continuous drive, and there we will see how things match with some numerics. And then in the second part I will discuss a setup in higher dimensional CFTs. So same setup we can import in higher dimension CFTs, which will allow again for exact solution, and again some kind of geometric understanding. So not everything is understood, that's why we still are working on it. And finally we will try to understand this non-equilibrium spectrum, which is responsible for these interesting steady state behaviors. So usually when you do this flow case, so usually the system heats up because the energy is being put into the system, so one expects that it will be a thermal state. But we'll see that due to the theory being conformal, so nothing to do with holography, but just being conformal, it will have some special phases where it will prevent this thermalization. Okay, that's the surprise, and that's what I want to tell you guys, show you guys. Okay. So this is the setup. So H0 will be the CFT Hamiltonian in 1+1. So we'll take it on a circle. So there will be a C by 12. And then, so one can write it as an integral of the stress tensor, the TT component. And then H1 will be a deformed Hamiltonian, which is the sine square x over 2. So this was studied as early as 2001 by some condensed matter physicists, because if one thinks of this as a lattice sum, then what this term is doing is it's decreasing the weight of the boundaries. So if one is interested only in the physics inside the chain, then this was a thing that they played with. And what they found, yeah, I don't have it. So what they found, so they looked at, so they did it for open chain. So from site 1 to n. And what they looked at was the finite energy density. So they looked at En, the finite energy corrections to the energy density. So En over n minus limit n going to infinity En over n of the ground state energy density. So if there was no deformation, then, and they did it in a hopping model. So if there was no deformation, the finite n corrections go like 1 over n. But in presence of this deformation, they found that it changed to 1 over n square, which is what happens if this is a closed system, if it's periodic. Okay, and this this was suggested as a way that the boundaries go away. The boundaries don't matter at all, and this kind of periodicity we'll see will be able to explain naturally in context of CFTs. Okay, so this was the setup, and a lot of people have worked in this area. So we'll recognize many names. So some of you may be here, and sorry if I missed people. Okay, so this is the setup, and it can be solved just by using conformal maps, because once one goes to the plane from the cylinder. So let's say you start in the cylinder, we go to the plane. Once we go to the plane, one realizes that this Hamiltonian is just made out of L0 and L1 and L minus 1. Yes.
Both without the sine squared and with the sine squared?
No. 1 over n was without the sine square. So it was open chain. That's what is expected for an open chain. And then 1 over n square is with the sine square deformation.
But you can also consider periodic boundary conditions without the sine squared.
Yeah, so here they were considering open. Yeah, then if you had periodic, then you would get 1 over n square.
In both cases?
Yeah.
Okay.
So
can I ask a question?
Yes.
So how much can you really forget about the boundary condition if it's a lattice system?
Yeah, so I'll come back to this point. We'll see that there are observables where the boundary conditions will play an important role.
I see, thank you.
Yeah.
Instead of sine square, let's say I put another function which also decays at the boundaries. Would I still expect this sort of a behavior? 1 over n going to 1 over n square or something similar?
This I do not know the answer, but for sine square, what I'll be using the fact that there is a SL2R here. Okay, so there can be other functions where you can get LQ, L minus Q. That's also SL2R with L0. So those classes of functions are what will be considered, but in general it will be made out of some generators. So
I have seen some paper. I've seen some paper saying that if you deform it by sine to the alpha, you get into the into the alpha minus 3/2 or something. I forgot, but
yeah, probably. Yeah.
Right.
Yeah, but here I'll be just considering sine square. And I'll be also, so in most of the cases, I'll be looking at the cylinder, because I really want to show how the geometry can explain the dynamics. Okay, and then once it is written in terms of this SL2R generators, then it's just using the algebra, and then over the full time period, so these are Euclidean evolutions now, tau 0 and tau 1. And using SL2 algebra, one can bring this product into a single L0, L1 and L minus 1 with coefficients C0, C1, C2, which will be functions of tau 1 and tau 2. Once this is done, then this is part of the global group. So one can do a Mobius transformation and go to a different frame where it looks like a L0. And then one knows how to evolve in this frame, and therefore one knows, once one knows these Mobius parameters, which are functions of C0, C1, C2, and therefore of tau 1 and tau 0, one knows the conformal transformation, which takes to this final flat slicing. Yes?
Just think of this as like evolution seen by some, in a trajectory which is just turning on and off a rocket, like on, off. Because
so these are some different slicings of time.
yeah, but you periodically swap, I mean change
So
slicings,
periodic
right?
or not, it will depend whether, so it will depend on the parameters that will come to. That whether you will come back to the same point.
No, I mean H and H1, like
Yeah,
you're
H and
slicing.
H1 is alternating. So that's why you have these, this matrix, transfer matrix, you can think of this as transfer matrix raised to the power n. So, but what will happen is this map gets iterated. So it's a map to the, from the plane to the, from the cylinder to the plane, and then a series of Mobius maps. So these maps just gets iterated. And because it is a Mobius, it's easy, it's well known how to iterate this map. Okay, and that will connect to the geometry. So once we know this transformation, then any observable we can, with a definite weight, we can evaluate using its conformal properties essentially. So the space-time dependence of the observables can be determined via the behavior under conformal transformation. Okay, so it's just through these transformations where one can do it, and for n cycles, one will just have to iterate this map. And for observable of weight h and h bar, weight h, just here, just the holomorphic thing is shown. So one just evaluates the derivative of this Zn to the power h, and this is the factor coming from the cylinder to the plane. And one, of course, will have to express this in terms of the original cylinder coordinates, or original cylinder angle and time, because that's the physical setup. Okay, and few things about the Mobius map. So the map can be written in terms of its fixed points. So basically these are the fixed points of the Mobius map, and there is this parameter eta, which will play an important role, which is made out of CD, and basically the fixed points appear in this way. And the fixed points can, as you see here, the fixed points can either be real or complex, depends on the sign of this. And if they're complex, they are conjugates of each other, or they are just two real solutions. So this eta, and one can work out this, if this is complex, then this eta has absolute value 1. It's just a rotation. And if one iterates it, then one gets, so basically, if I iterate it twice, then it will be eta, and then I have to do a map again on z. I use this formula again, I get eta squared and so on. So for if I iterate for n cycles, I'll get a factor of eta power n. And n is, remember, the discrete, the stroboscopic time. So the observables are basically going to be, so if I now take a derivative, I'll pick out this factor, because it's a multiplicative factor. So I'll pick out eta to the power nh. And this is what is happening. So suppose these are the two fixed points. So this map, first map, you can think of sending one fixed point to 0 and another to infinity. And then any point here will transform. This is called this S of z. It goes here. And then there is this eta, which can have a radial part, a scaling and a rotation. So it can either scale, so it will scale this radially, and then it can rotate. But if it's just rotation, it will just move it around these circles. And then you again bring it back, so you land up somewhere here. So this is how it geometrically Mobius maps looks like, Euclidean Mobius maps look like. And now there are two cases. One case when these fixed points are complex and they have unit norm. In that case, basically this is only rotation. So then if you are in some point away from the fixed point, you just go around. Just go around it. So this is the case which will be this case where one has periodic behavior of observables. And the other case is where this is real, so then one flows from one fixed point to the other fixed point. Okay, so these are the two situations. And these are also mapped to the conjugacy classes of this group, because the conjugacy classes are mapped by the fixed points in this case. So this is Euclidean, and then the consequence of this, as I was discussing, is that if we are close to one of the fixed points, then this factor will give me a eta power n. And then in unitary theories where h is positive, this will lead to some exponential behavior with n. So observables will exponentially grow or decay. So in some places it will, so near one fixed point things will grow exponentially with time, and in other places it will decay exponentially. So the inhomogeneity will get magnified in any quantity. Okay, so this is an interesting effect that happens in the case when eta is real. When eta is imaginary, it's just periodic motion. However, we are interested in the Lorentzian case. So this was all Euclidean. So we have to really analytically continue. And these dynamics don't change that much. The locations of the fixed point changes when I analytically continue. So then Z Lorentzian itself lies on the unit circle. And in the elliptic, in the case of this complex roots, in this case, one of the roots lie outside the unit circle, one lies inside. So the dynamics can never reach any of these roots. So if I start from any point, I just keep going around. As I change n, as I stroboscopically evolve, I just move around this circle. And in the other case, the fixed points lie on the circle, and then I go exponentially fast in one of the directions. I reach from one fixed point to the other fixed point. So whichever is the closest, I reach that point, and that gives exponential behaviors which magnify this inhomogeneity in the system, spatial inhomogeneity. But in this case, it just goes around like this. So this is what happens in Lorentzian dynamics. And if you track, so one can track what is happening to the position on the compact circle and time after each stroboscopic step, and one finds in this case, when the roots are complex, then one just goes around and repeats. One falls back on the position where one started it. Whereas in the other case, one goes, if one is away from one fixed point, one quickly, so there's accumulation of points, so one stops moving. So it's like thermalization. So you stop moving, you don't do anything after that. So that's the hyperbolic case. So this is what happens in this 2D, and this is the geometric understanding. Any questions about these geometric pictures? Yeah.
Bit lost. So you had this time-dependent Hamiltonian that you're evolving.
Yeah.
These things you are plotting are just showing how the map is changing as a function of n, but
Yeah.
or is it some plot of some observable?
No, I will come to the observable now.
Okay, so
I
you
was
were
just
just showing
looking
how
at
the complex plane is being transformed as you do more and more.
just the geometry.
Okay.
Yeah, now, great. So now I come to observable, but before that, let me just mention we can also do it if the drive is continuous. And if the drive is continuous, then the phase diagram is richer in the sense that, as a function of the drive frequency and the amplitude, this delta f, one has this kind of a phase diagram where these rate points are where one has exponential behaviors, where the roots are real, and these are where one has oscillatory behavior of the coordinates as a function of this stroboscopic time. But we will see that observables will follow such behavior. So observables here will have a exponential behavior with time. whereas observables here will have a oscillating behavior. Okay, so for example, this is an observable, and this is some comparison with lattice. So this is just free fermions hopping, and here you see this term. This is the sine square deformation basically, because this coupling depends on the position of the lattice in exactly the way you will have in a sine square case. So it's cosine of 2. And then in this case, you can look at the energy density in this evolving state. So the evolving state will be obtained by acting with u n times after n steps, and then you measure the tau component of the stress tensor. And so one thing to notice is that if you start with a vacuum, then because the dynamics is L0, L1 and L-1, nothing will happen because all of them annihilate the vacuum. So to get something non-trivial, you have to start with some other state, non-trivial state. So here, let's say this is a primary state. So then what happens is, if you are in the hyperbolic phase, where the roots are real and you have these exponential behaviors, there at time 0, if I start with a uniform density, because at time 0 the primary state has uniform energy density, then as time increases, then you have localization at the fixed points of energy density. And this is some plot at very late time, and you see, so these are some lattice results, and these are the CFT results, and we have taken this to be the primary. So half is just you excite one on both sides of the Fermi, half filled Fermi surface. And this is the energy in the other phase where you have oscillatory behavior of energy. Okay, and there's a boundary which is Pawel law, and there's exponential decay. So it depends on which phase you are in this diagram, which you can control by tuning delta F and omega. Okay, and then one can also look at entanglement entropy, and one also finds, so I will not go through this one. So here one doesn't know the full answer because it's a 4-point function, and because one looks at entanglement of excited states, and when one is in the elliptic phase, one can show that the cross ratio after n steps, it approaches 1. So one can expand the correlator in the dual channel, and one can figure out what is the universal contribution, and one can show that it is oscillating with n, with time, entanglement, and in transition. But in, of course, in the hyperbolic phase, then one doesn't have, one has to work with the full conformal blocks. Yeah.
Terminology question. So this non-heating phase is the oscillating phase that you...
Yeah.
And in what sense is the other phase heating? What is getting heated?
Yeah, so what is getting heated is in the sense that energy, if you measure temperature here, for example, energy density at some places is rising. Of course, there's cooling in other places. In that sense, it's called.
Some portions are getting heated.
Yeah, some portions are getting heated.
And this E of x over L is the energy density.
Energy density. Yeah. What is the periodicity? Yeah, so the periodicity is a complicated function. So because it will depend on all the parameters in a non-trivial way. So we have an answer for that.
But the periodicity changes from the original drive?
Yes. Periodicity changes. It depends on the state, actually. The periodicity depends on the energy of the state also, which you are driving.
Yeah, I mean, like generally, if you get this kind of thing where the periodicity become, let's say, larger or something, right? So that you call time crystal.
I see. Here one can engineer that by tuning omega and delta F.
Okay.
Okay, now I'll just borrow whatever we did in 2D into higher D, because in higher dimension there is always a SL2 subgroup in a CFT. And this is the second part. So now, once again, if I consider a drive like this. So for 2D, we got this drive starting from the sine square and we could write it using the SL2R. But here, by fiat, we'll have this drive, this SL2R drive with some parameter beta. So I'm working in this yellow book convention where ID is Hermitian. And then in terms of the Euclidean time on the cylinder, so now I have a cylinder on, so D plus 1 dimensions, yeah, so R and SD, and W is this R, the real, the time on the cylinder, the Euclidean time on the cylinder, and this is the evolution operator. This pi represents, so now I have a choice of which SL2R to choose, just like in Virasoro I had a choice of choosing which non-zero L to choose along with L0. So here these are mu directions, so this is just mu, pi projects to that direction. And then again I can use Beckel-Campbell-Hausdorff where I can factorize them, and then I can figure out the transformation because I know how each of them will transform my coordinate. So for example, this is a special conformal transformation, this is a dilatation, and this is just the translation. And so then one can write down these transformations, and one can again repeat the steps. But there is but it gets very complicated, and therefore one looks for simplifications in doing this. And there is fortunately a way to do it in a simpler way, which is by using quaternions. So in 4 and lower dimensions, this representation is quite useful. In higher dimensions, one can write, in the embedding space, one can write representations and do it, but quaternions are quite useful in 4 and lower dimensions. So now, basically, one organizes the space-time coordinates into a 2x2 matrix Q, the quaternion matrix, and then conformal transformations act like Mobius transformations, Mobius matrix transformations. So these A, B, C, Ds are now matrices, quaternion matrices, obeying this determinant condition. And these are all 2x2, so there are 4 of them, so, and with one constant, so there are 15. So which accounts for the conformal transformations in 4D. And usefulness of this is one can again do this iteration. And then the final parameter, final matrices, final quaternions which describe the transformations are obtained by just doing matrix multiplication of this ABCD matrix. So and this one can do this and check with the explicit answer, with these answers, that you get the correct answer. And a little more about slightly, okay, I'll not spend time about this. So I just wanted to say that there is a choice here, because a quaternion has identity and polymatrices, so one can always do a global rotation here, and that doesn't change anything. So it's arbitrary where to which coordinate you associate which polymatrix. So this formalism is impervious to that. So, and then once again you have this quaternion matrix, and then you find out, so this gives you the conformal transformation. So now of course the cylinder to plane is no longer conformal, it's a voil. So things with anomaly you have to take into account, but after you go to the plane, then you can use this generalized Mobius map to figure out where you are. And then one can compute several things. So one thing, for example, interesting thing to compare is the fidelity, which is if I start with a state and I evolve and I take projection with the state, then do I remember the state or forget it? And here what we are doing is we are deforming first in the Euclidean time direction, then in the 3 direction, and then in the 1 direction. We are going back in the 1 direction, and then looking at this overlap, and there is this parameter beta, and once again we have a notion of heating and non-heating. So what this plot indicates is in the beta and t plane, what is this quantity, the mod square of this quantity. And you see that this dark color is almost 0. So the state is this inner product goes to 0. So beta greater than 1, there is, so the system seems to thermalize. And whereas for beta less than 1, there are oscillations and the fidelity almost reaches 1 for some times. Okay, so it almost comes back. So, and this one can actually determine also analytically. So these are the times where it almost comes back. And one can look into localizations of energy density again. So it's similar calculation, just mode indices to keep track of. But one can see again energies. So this is plotted along the time and some cylinder angle. And one sees along some angle there is oscillations happening. And whereas in the other phase, beta greater than 1, there is localization happening of the energy. So energy peaks up at some points. And basically energy peaks up like this. So at very early time, this is, so for small n, so I'm just plotting this. So at small n, this is the green line, it's almost homogeneous. So I started with some primary state, then as n increases, one has localization at the fixed point of the energy. So this black line is the thing at the latest time. So the same thing happens. And one curiosity is that for the beta less than 1 case, one can always write this as a cos h in front of d and a sinh in front of k plus b. So one can always find a unitary transformation to the usual Hamiltonian, the ID, which has a discrete spectrum. And because this unitary exists, so one expects that one will have these periodicities because one has discrete spectrum. However, for beta greater than 1, no such unitary exists, which will take it to ID. So the best thing one can do to go to a known Hamiltonian is this Lusher-Mack Hamiltonian, which is analog of L1 plus L minus 1, which is using this unitary. And this is supposed to have a continuous spectrum, continuous non-degenerate spectrum. So this may be a reason why one sees this effective thermal behavior. Phase diagram can be richer because here I had only beta and only 1t, but one can do a more general drive where one can have ID for t less than t1, and from t1 to t1 plus t2, one can do a deformation. In that case, one finds these puddles where inside you have heating, outside you have non-heating. So depending on the value of T1 and T2. And again, once again, there is a nice geometric understanding from the point of view of fixed points in the Euclidean picture. The structure is richer. So this is in 2 plus 1. So in 2 plus 1, if you look at the fixed points, you can have fixed surfaces. So what was analog of the elliptic phase, the oscillating phase, now one has fixed surfaces which is some value of x. So this is when you deform in the x direction. So some value of x and some value of y square plus tau square have to be constant. So that means this cylinder is intersecting this plane at x. So this circle is a fixed point, and if you track the motion of anything starting any coordinate which is starting close to this fixed line, and you track its motion as a function of n, you will see that it goes around. So it intersects the cylinder somewhere, but it goes around, it winds around this circle. So that's the picture in higher dimensions. So this is in 2 plus 1, 3 plus 1, similar thing will happen. And there is again a story of classifying the dynamics using these geometries. But this is Euclidean, and in Lorentzian things are a little more complicated. So that we have not explored. And so this is something we are trying to understand, and I'll just finish by saying a few things about the spectrum. So this paper we noticed recently that has proven that this operator has continuous spectrum, and the proof just is also geometric. So any conformal transformation can be mapped because the identity map is just Z. And in free boson, one can verify using truncated numerics. So one knows this in free boson. So in free boson, for example, on the cylinder, one can do these maps. So from W I go to the plane, from the plane I go to the Mobius, and I have that's a plane, and that has its corresponding cylinder, and it has modes, and one can find a non-trivial relationship between these modes, and one can check the energies. Yes.
So when you say the Hamiltonian is L1 plus L minus 1,
Yeah.
I thought it would be on the Hilbert space of a line and this is the momentum operator. But is the point that it's L1 plus L minus 1, but the it's still on the Hilbert space of a circle?
Yeah, because I'm measuring energies in the circle. That's my original system. That's why, because if it's in this new slicing, that's again, in that slicing, it is again some L0.
Okay.
So in terms of those energies, it's again, in terms of those times evolving in that time, it's again some discrete spectrum. But I'm doing my experiments in this original theory, W.
Okay, thank you.
It's also modular. So there's a connection also with modular Hamilton.
Okay, thank you.
And so this is when there is only L0, so one sees unit-spaced energies with degeneracies, and once one looks at this deformation, then one gets this. But if one looks at other measures like Krylov level spacing, they are integrable because this is still a quadratic. Okay, conclusions. So of course holographic interpretations. So one way to do it may be to solve the Killing equations and find how these time slices extend inside. So okay, the question, is there a horizon for this heating phase in this induced metric on these time slices? So that's what people seem to find in 3D, but 3D is very special. So in higher dimension, one should be able to explore this. And then this is something we are actively trying to do. We are trying to classify the phases now using the conjugacy classes of SL2H, which is this group of these Mobius matrices. And mathematicians have classified the conjugacy classes, and so we are trying to identify driving which phase will give us what kind of behavior. And then it will be interesting to understand the spectrum. And then what is different from if there is a chaotic CFT. Okay, so at least means from the point of view of spectrum. So this paper actually tries to ask these questions. Malvimat, Somnath, and Boishali, Vinay here. So, and they find interesting answers, universal answers in context of 2D CFTs for Krylov complexity. And then there can be, as someone mentioned, there can be applications to the modular dynamics, because modular dynamics also lies in this group, at least the boost operator. And then, for example, it can be relevant in computing quantities like this, whose geometry correspond to this double cone. So, for example, this has to be regularized, and then one generates already 2 elements of the SL2R. This appeared recently, this paper. Later. Yeah, so with that, I'll finish.
We have a lot of time for questions.
Higher than 4 dimensions, can you use octonions?
Yeah, that's what. Yeah, so I think one can use octonions, and basically Clifford groups one can use for higher dimensions. I think there is a paper on conformal integrals by Kaushik Rai and others where they use some of this octonion technology.
And this fails beyond like 8 dimensions or something.
Maybe then you have to use Clifford groups in a clever way.
Okay, so that's the generalization. Okay, thanks.
Yeah.
Yeah, these two papers, they seem to be identical, and they both were published in the 42nd month of the year 2022, but that's... But my question was not about that. You made a reference to whether the spectrum is chaotic or not. I probably missed something, but if you just take in the primary or something, then you're just in a single representation of the conformal group, and it could not care less about whether it's chaos. Are you having in mind thermal quenches, or applying it to thermal states, or what exactly is the place where chaos becomes relevant?
So, yeah, so I think, so what these people found is in large CCFTs where the identity block dominates, then they computed the Krylov complexity under the drives, under these drives, and they found—
In which state?
So in the sense of, they looked at Krylov operator complexity. So
for a primary operator, or?
Yeah, primary operator.
But would that still not keep you essentially in a single orbit of the conformal group? Because you commute the primary of the Hamiltonian, and all these Hamiltonians live in the conformal group, so it seems like you're still in a single representation.
You will be in the...
And that is precisely not where chaos happens?
You will be in the same representation, that is true. That is true. So I know one calculation which takes them out of the orbit where they look at operator complexity, but in some non-trivial states. So they redefine their notion of the trace. So there they get the 4-point functions appear. There they have, and there what they find is in the hyperbolic phase, they have exponential growth of complexity, whereas in the other phase, they have oscillations.
And what was the state in that case?
What the state was some excited primary state, heavy.
But you use a perturbation that's not in the conformal group in that case?
Yeah.
Okay, thanks.
I think so.
More questions?
Does this Floquet CFTs have some, like, supposed to represent some holographic duals? Like, what happens on the gravity side? Like, is anything known about them?
So only in, I think only in 3D.
Okay.
I think so the induced metric, so because now it's just observer is moving in some different time slice, not changing the geometry. You are changing how you are evolving in time, what you are calling time.
Yeah.
And then in these time slices, sometimes horizons can appear, so that observer can see, probably can see horizon.
I see. Thanks.
So to our subdriving?
Very interesting. So one question which I don't know the answer is if I, because these quaternions generate the entire group, at least in 4D, if I keep driving in different directions, using different SL2Rs, will I cover the entire group? That is an answer which I don't know.
Okay, thanks. It's interesting.
So one way to go to different groups, different directions, is one has to always orient the quaternion, and that can again be done as a change of basis. So that can also be brought in a quaternion format. So it gives hope that one can explore this.
Okay, so let's thank Diptarka once again.